Welcome everyone to our bioelectrodynamics webinar number 32. So for those who haven't attended yet, the policy is that we have the attendees muted and with the videos off during the talk. If you have any questions, please type them to the chat or to the Q&A section in the webinar, or also you can raise your hand after the talk to ask the questions. So the lecture is recorded, including the Q&A session which will be recorded, and then we'll have that uploaded to our YouTube channel. So the talk is expected to last about 45 minutes. And with this, I would like to also thank our regular supporters, and that's the International Union of Radio Science, URSI, and also our IEEE Czechoslovakia section, particularly the Engineering and Medicine and Biology chapter. I would like to introduce our today's speaker, who is Mohammad Abdolrazzaghi, who is the IEEE member, and he earned his bachelor degree in Iran University of Science and Technology, and then later on his master degrees in the University of Alberta. Currently, he's pursuing his PhD degree in the University of Toronto, and as you will see, his research interests include microwave sensors, dielectric measurement techniques, wireless power transfer, and so on, and importantly also the machine learning. He received several scholarships for his PhD, and he has been really productive. So and also invent a lot of many interesting inventions coming from Mohammad. So without further ado, Mohammad, please, screen is yours.
Yeah. Thank you so much, Professor Michael, for your comprehensive introduction, and I appreciate that. So hi, everyone. I'm Mohammad Abdolrazzaghi, and I'm here to present my talk on advances in microwave planar sensors using active circuitry embedded with ML features. So let's dive into the outline first. So I'll go over the background in the microwave sensors, and I'll talk about the challenges related to the low to moderate quality factor as well as the sensitivity with the susceptibility of the microwave sensors to an environment. Then we'll move forward with the introduced methods to overcome these challenges using the passive sensors first, and then we'll try to incorporate some active sensing ideas, followed by the machine learning techniques. So as we have seen in the literature, that there are so different types of sensors around us in our daily life, and we have been full of different types of temperature sensors, pressure gauges, distance sensors with accelerometers, and all types of sensors. One of the main types of the sensing mechanisms around us is on the material sensing, which has its impression and application in a wide range of places, including environmental monitoring, food industry, military, and medical diagnosis. And for the material characterization, there are also different types of sensors. In our discussion today, we'll be mostly diving into the microwave platform for material characterization, among the other available electrochemical sensors or other the chemical reactors, mainly because of several reasons that, as you can see on the screen, microwave planar sensors allow us for the non-contact sensing of the material in harsh environments or in rural areas that there's no direct access to the material. Also, they can be wrapped around different products in the quality monitoring purposes, or they can pass through different layers of the material and allow us to intercept the information in deeper layers of a given environment. All of them are some of the benefits of microwave sensors, and it comes more practical when they are embedded into wearable devices, as you can see in the bottom right, that could be wrapped around different parts of the body, mainly because of the flexible substrates that are being used. However, there are some challenges associated with the microwave planar sensors, and that's some of them are these low to moderate sensitivity and quality factor that we're about to discuss the challenges first. So one of the typical types of the resonators that we are using in microwave sensing is a split ring resonator, as you can see here on the bottom left. So in general, there is a capacitive region that is sensitive area that is sensitive to the environment around that, and it allows us to interfere with the environment around us and intercept information about any variations. A typical sensor transmission response could look like this bell-shaped structure, as you can see in the blank part, which means that there is no material introduced to the sensor. However, when there is any effective medium introduced to the sensor, there is a change in the response of the sensor that goes for both the magnitude and the phase and the whole transmission response of the sensor that typically it shifts downwards in frequency. However, the chances are that when there are slight variations in the environment, for instance, the effective permittivity of an introduced element is about 20 compared to 20.5, the response of the sensor is not going to be as sensitive to be able to distinguish their variations. And we are dealing with mostly overlapped responses. And that's one of the challenges associated with the microwave planar sensors that are not highly sensitive to the environment. And also it comes with the associated low quality factor. As you can see here, the peak is not as sharp as possible to allow us to distinguish these two curves easily. That happens for a wide range of microwave planar sensors, including the complementary SRRs or extended gap SRRs or carved SRRs, as you can see some of the examples on the right side. So we are about to elaborate on some of the techniques in passive domain of microwave sensors, that how we can overcome these low to moderate quality factor that allows us for better sensing of the environment. To start with, let's get to the details of one of the techniques that we have developed the past few years, and that is on the coupling of the SRRs with the feed lines. And essentially, a normal transmission line that is going to be coupled with the SRR is shown, as you can see on the bottom left graph, and it can be analyzed with the signal flow graph as well. We have found out that if you consider the coupling between the transmission line and also the resonator to be known with CC or DC coupling, and also the gap capacitance, that is the main area for us to analyze the material as C gap, there is a relationship that as the CC increases, you can see with these graphs that when we move to the black curve, compared to the C gap, for normal material characterization for a wide range of permittivity values, we have larger shifts. That's something that we have theoretically analyzed, and we verified that in simulation as well. That is mainly because when the material is going to cover the sensitive area of the SRR, it also covers part of the coupling region between the SRR and also the surrounding transmission line. And the higher the coupling, the higher the effective impact of the material on the sensing. So we have tried to increase this coupling between the SRR and also the surrounding transmission line to be able to exploit this property. In order to do that, we have used a technique in microwave engineering that is mostly on the metamaterial part, and that's how you can increase the coupling between a pair of transmission lines when one of those transmission lines is not a typical one, but a negative refractive index-based metamaterial transmission line. So in order to exploit and deploy such a transmission line, we needed to load one of those transmission lines with series capacitors and parallel inductors so that it could represent proper metamaterial properties or negative refractive index properties. As you can see here in the bottom, dispersion characteristics, so we could design such a transmission line pair that could work at a frequency of around 2 to 3 gigahertz with just loading one of these transmission lines with series capacitors and parallel inductors. In that case, these feed lines are no longer going to be normal transmission lines, but they are metamaterial transmission lines. And in that case, you can see on the simulation results on the right side that the conventional sensing paradigm that happens for permittivities from 1 to 30, we have a certain range of frequency shift for a given material. However, when we change the transmission type from a normal one to metamaterial-based transmission line, we clearly see a much wider variation in the transmission profile that allows us for increasing the sensitivity of such sensors in general for a wide range of applications. So we have implemented such a sensor, as you can see in the bottom left figure, with loading the input-output transmission lines with series capacitors and parallel inductors. And we have shown that for a wide range of permittivity values in simulation, the characteristic curve for this sensor, as you can see here with this circle dots, the characteristic curve shows sort of planar plateau variation when we are dealing with relatively high permittivity values. However, when we change the typical transmission line to metamaterial transmission line, we see that this plateau shape is going to show up much later, and we are exploiting a much more linear part of the transmission line and the sensor for much wider range of frequency permittivity values up to around 70, 80, 90 that we are dealing with water mostly. And over here we have some simulation, some measurement results showing that when the host material is water and we are trying to sense much small variations of methanol and ethanol in the ppm level, in stepwise over time, we could show this measurement result with two different types of sensors. One, so with the conventional sensor, as you can see here at the bottom curve, that there is no much distinction between them because the variations are very small and the host permittivity is much higher. It's around 80 when we're dealing with water at the frequency of 1.8 gigahertz. And comparing that with the results obtained with the metamaterial induced transmission sensor, as you can see here, these steps are clearly distinguishable for both methanol and ethanol. That's mainly because these variations, even if they are small, they are sitting at much higher permittivity values, around 80, that the sensor response shows a still somewhat linear response over here compared to conventional sensor response. So this is one method that we could show how we can increase the sensitivity of microwave planar sensors still in the passive form factor in order to allow us to sense small variations. So moving forward, we're developing some different types of sensors. In this case, we are working on the mechanical sensitivity enhancement. So we have seen different types of sensors in the literature that are used for displacement sensing, rotation sensing, stretch sensing, and all of these type of mechanical variations. However, we have developed an electromagnetic sensor that also allows us to get all of those mechanical variations, but with much higher sensitivity. And the way to do that, we have started with a pair of double splittering resonator, as you can see here on the left graph, as the basic part of a typical resonator. And it has characteristics, transmission profiles, as you can see here in the middle graph. And later on, we have coupled that with another pair of splittering resonator, double splittering resonator on the top layer as well, with 180 degrees phase shift in sense. And we'll study that later. So essentially, this structure is not a single layer, but two-layer structure that are coupled with each other. And that allows us to engage the variations in the environment much more. The way that we have exploited that is with different type of sensing, as you can see here, starting with the vertical separation sensor. There are two layers that are separated with a plastic pivot at the central part, and those splittering resonators are going to vary in distance with respect to each other, as you can see in the measurement setup as well. And we have shown that their transmission profile is going to be impacted significantly for the distance between these two layers when they change from 0.1 millimeter up to 1 millimeter. And over here, we see the characteristic curve for the sensor that shows a significant variation and still robust operation for small variations such that the resonance frequency change all the way from about 2.5 gigahertz to 4.5 gigahertz. One more type of mechanical variation that we have studied is on rotation. As you can see here, when the two pairs are on top of each other, but one of those pairs are going to show a variation in the rotation or the angle that they are superimposed on each other, we can show that for a wide range of angle deviations from 0 degrees all the way to 180 degrees, and also minus 180 to 0 degrees, there is a sort of linear variation in the frequency response from around 3.7 gigahertz all the way to 4.5 gigahertz. And that's repeatable for both sides and quite reliable in terms of the uncertainty that you can see in the graph. We have tried the same idea for displacement sensing and also stretch sensing that I would just suffice to call the linearity of the sensor in both cases, as well as high robustness that we have achieved for a wide range of lateral separation and also stretch. Moving forward, let's discuss more about the active sensing, how the active sensors have helped us in increasing the sensitivity and reliability of microwave sensing. So let's take a quick look at the theory of what we are after with active sensors. Let's start with the passive sensor for a bit. As you can see here, here is a simple split ring resonator with a blue line that is coupled with a pair of transmission lines, and we can have a typical transmission profile that is shown with a black curve. However, we found out that the low quality factor of such planar microwave resonators are either because of the surrounding medium or because of the radiation of the electromagnetic power into the free space or from the substrate loss. And all of those are going to be counted and compensated with active circuitry. And the way that it works is that we are going to take a sample from the microwave power from the normal capacitor, the split ring resonator, and we're going to add and amplify that power and return that to the resonator at the right time, such that all of these circulation of the power with enhancement in its amplitude are going to interfere with each other constructively, and that construction is going to help us to increase the sensor performance in terms of the quality factor. As you can see here on the right graph, the red curve shows that how enhancing the quality factor helps or employing the active circuitry helps us to get a high quality factor in the sensor response. This is implemented mainly using a transistor in the RF domain in the regenerative amplifier configuration, as you can see on the left graph. And in terms of the electromagnetic behavior and electric field propagation to free space on the bottom, you can see that as the quality factor increases, the electromagnetic fields are going to propagate much more into free space, as you can see on the bottom right, which allows us actually to interpret the information of deeper layers of material or further distant materials when we're employing active circuitry. So we have implemented such an active circuit in active sensor at a frequency of around 1 gigahertz, and we using the regenerative technique that we just discussed. And we have placed a material on top of the sensitive region of the sensor, as you can see here, using PTFE tubing and all of those variations. We have tried a simple test on a material that is going to be injected inside this tube that causes this whole transmission profile to shift to the left by value of around 1 megahertz, as you can see here. And we did that on 2 cases of passive and active in order to show both the change in the quality factor and sharpness of these curves, as you can see how distinct the active profiles are compared to the passive profile. And also another important feature that we realized and verified indeed is that the material variation was exactly the same, and the sensors could verify that as well, even if we have changed the modality from the passive to the active, but the variation in the sensor response hasn't changed, which means that introducing active circuitry into the circuit doesn't increase or add more to the sensitivity of, or doesn't reduce the sensitivity of the structure, even if there are some active elements involved. So that's one of the advantages of using the active circuitry, which doesn't reduce the sensitivity, but just increases the quality factor and helps us to have much better resolution in our sensing. Here is the diagram showing that how the active circuitry helps us to come to overcome the internal losses that are represented with GMUT and GI, as well as the external losses, GMUT, GI, and also GE. We know that with partial compensation, we can achieve the active resonator behavior. However, if we keep increasing the compensation, we could get into the region that not only we have an active resonator operation, but also there will be some oscillations involved in our circuitry. So we can discuss about that later more in general, but here are the 2 modalities that we could have. We're mostly interested in using the sensor in active resonator mode. So we have used this technique in some of the high-end sensing applications that what mattered for us is distinguishing the small variations in the environment. And one of the main applications is oil sand industry, where small quantities of asphaltene is going to be understood and intercepted in the environment, such that if there is a chance of clogging in the pipelines and oil sand pipelines, there could be some information, the onset information, much earlier than the clogging itself. And if we could understand and extrapolate the precipitation of the asphaltene in the pipelines, we can predict that if there is a clogging in the pipeline or not. So the idea is to be able to understand these small variations in the precipitation of asphaltene, which is quite difficult because the variations are in the ppm level. For that, we have employed an active resonator, again using the regenerative sensor technique, as you can see here. And we have used, again, a PTFE tubing that allows us to pass through some oil sand quantities and samples, such that in this case, we are mixing heptane with asphaltene solution. And heptane is a precipitant that allows the asphaltene that is already dissolved in the oil sample to be precipitated. And that happens over time, as you can see here. At the initial stage, this tube looks quite black, but after a while, you see that the tube seems to be clear because those asphaltene has already been precipitated and extracted from the whole volume. So this behavior is verified in our sensor as well with a change in the resonance frequency. As you can see here, that there is a distinct increase in the resonance frequency only because the variations are small enough, as you can see here, in the range of sub-megahertz, that only active sensor is able to intercept that. And with passive sensor, we could not see such a change in general. So that's one of the advantages of using the active sensor. Moving forward, we have used this technique in a little bit more involved application of oil sand industry, and again in dispersion coefficient, which needed to analyze the behavior of the precipitated asphaltene in 2 places, not just one, such that the distribution of that precipitation in the sample is going to be analyzed, as you can see here. So in order to accommodate for that, we designed two uncoupled active sensors, as you can see here. And for that, we have designed it such that if the tube is going to pass through one of them at a time, after a while, a much wider precipitated sample is going to pass through the other resonator. So in this case, the two resonators are going to be engaged in the formation of the resonance frequency of both of them are going to be analyzed. And you can see on the right side graph that we are dealing with two resonant type behavior, that one of them is for the first resonator, and the next graph is for the second resonator, which shows that the sample is passing through for the one of the first and then goes through the second one. And because of the differences in this in the expansion of these curves, we can find out the diffusion coefficient, as you can see here. These values match very well with the values obtained by other standard techniques in the literature as well, that shows us how we can also use active sensors to elaborate on the dispersion monitoring. Moving forward, we have developed some other techniques other than the active resonator itself. And we found out that we could not only partially compensate the lost power, but also we could move forward with full compensation of the active power, and that allows us to use microwave oscillators rather than active resonators. And oscillators have the benefit of having only one output, that reduces the complexity of using expensive DNAs in order to analyze the sensor response. Over here, here's an example of how we have analyzed that. First, that if there is a resonator and followed by a capacitor, the phase of the transmission is going to vary. That helps us in finding out the perfect match in the phase diagram for full compensation of the active power, the lost active power. However, the frequency doesn't change, which is what we really need in a sensing application. We have implemented an active oscillator, as you can see here, at a frequency of around 5 gigahertz. Fairly high frequency to allow us for better sensitivity in our sensing, and also a decent phase noise compared to the sensing applications that we have. So we have tried to use this oscillator behavior in humidity sensing, because again, humidity variations are going to be so small in the environment, and in order to analyze them, a very sensitive sensor is needed. In order to for us to monitor the humidity of the environment, we've used two mass flow controller to allow us for the controlling of the amount of the air that is going to be injected into a bubbler that controls the amount of the humidity of a sensor box. And that's how we are increasing the humidity of the box. And if you want to deplete the box from humidity, we use another separate air to just flush the air out of the humid air out of the box. For that, we have found and measured the sensor response as seen on the top right, that the oscillation frequency changes quite along with the change of the relative humidity. As you can see, they're overlapped quite well in both cases of increasing and decreasing of the relative humidity. It is noteworthy to mention that in this measurement, we have used some polyaniline polymer in order to absorb the relative humidity, because that increases the sensitivity of the whole sensor. However, we've used the active sensing mode in order to further increase the resolution of the sensing. That allows us to find out the high sensitivity of around 833 kilohertz for almost a wide range of relative humidity from 5 to 65%, as you can see on the right, bottom right. So once the oscillator is confirmed, we also needed to further increase the resolution and also the stability of the sensor, because microwave oscillators on their own are prone to being impacted by the environment, and their quality factor might change because of the changes in the environment, and that might reduce the stability of an oscillator in practice. We found that the phase noise of an oscillator, which is a factor to show that how stable of an oscillator is in frequency domain, is tightly linked with the quality factor of the tank that it uses. And in order to increase the stability, we need to increase the quality factor of the oscillator. So in order to do that, we have used the typical SRR in our structure for the transmission, and another active circuitry on the left side helps us to generate the oscillation. But beyond that, we have incorporated another active circuitry on the right side in a regenerative feedback mode, such that this P3 is only responsible to increase the quality factor of this resonator. And it's not going to impact the oscillation itself. It's only to increase the quality factor of this tank. So in a sense, we are using an oscillator with an active tank rather than a passive one. Here is a snapshot of the fabricated sensor, as you can see here. And the bottom right graph shows the responses in two cases where the sensor is using only the passive tank, as you can see how wide the resonance profile and oscillation profile is compared to an active tank. That not only the output power has increased because of the losses are compensated, but also the sharpness and the width of this oscillation behavior also has changed such that it allows us for a much more stable response and distinct from an adjacent sensor response. So here, we have used that technique in reducing the phase noise of a structure. And over here, we have tested it out in a scenario where in two cases of passive tank and also the active tank, different concentrations of water and ethanol are compared with each other. As you can see here, all the way from 3% to 50%, the sensor response is shown over time that has information of the stability of the sensing as well. So when an active tank is going to be incorporated, you see that how these deviations of the oscillation frequency and time are shrunk down to much more stabilized and single point, such that the sensor response is much more robust with respect to the change of the material, which allows us to be able to understand the much smaller variations. As you can see here, in these smaller variations of 3% or below, in the passive tank, we can't really analyze the information because of the relatively large free moving of the oscillation frequency. However, when the active tank is incorporated, we can go down to 0.5%. Or 0.75 or 1%, and they're distinctly separable from each other. And that shows the benefit of using the active tank compared to the passive that allows us to analyze the much smaller variations in the sensing response. Over here is another snapshot showing that how the uncertainty in the sensor response on the oscillation frequency variation in the passive tank, that could be anywhere between 35 to 40 kilohertz of free moving of the oscillation frequency, could be shrunk down and squeezed down to around 2 to 3 kilohertz when active tank is incorporated. So that's the benefit that we also can verify that with measuring the phase noise of an oscillator. And you can see that almost an improvement of about 13 dBc per hertz could be achieved when active filter is incorporated compared to the passive filter. So moving forward, we have developed a different technique for increasing the sensitivity of microwave sensors as well, and that is mostly getting the idea of inheriting the concept of oscillation, but working more towards that into the mixing. Imagine that we have not just one oscillator, but two oscillators working at a frequency of F1 and F2. And these two oscillators are separate from each other and they're not linked. However, if there is a variation in the environment that causes one of those frequencies to vary by the value of delta F, and F1 is going to decrease by that. However, F2 is not going to change because that's not going to be exposed to the environment and the material under test. In that case, if these two frequencies are coupled together in a mixer such that intermodulation products are generated, we can find the third, fifth, and seventh intermodulated product close to F1 as well. And the interesting fact about that is that the third intermodulation product shows variation twice as the original frequency. And the fifth intermodulation shows three times more, and seventh intermodulation shows 4 times more. So we have used actually the seventh intermodulation product, and that helps us to get 4 times more variation in the frequency compared to the original sensor. That's a clear benefit of using the intermodulation products compared to the original sensing the frequency to be able to analyze smaller variations. Over here, we're showing the basic idea of how that oscillation, the main sensing oscillator is fabricated. That works at a frequency of F1. And then here it could be fed with another frequency, such as F2, using a signal generator. And the output could show all of these intermodulated products. And as you can see here, when 2 cases of empty tube and the tube with water are compared, how the oscillating tones are changed when comparing with the original oscillator or the intermodulated products. Remember that this external input is not changing actually in this case. So that's the idea. And we have implemented another, a much more complicated form of the sensor, such that the initial constant sensor, the initial frequency of F2 that was fed externally using a signal generator is also generated using another active sensor. So this can be shown that it could be used either the first or later on. These 2 stages could be interchanged, but essentially we are dealing with 2 oscillating stages that are going to be mixed together at high frequency. And as you can see here, we have F1 and F2. When F2 is preserved constant and F1 is exposed to the environment, the initial frequency and the higher intermodulation products show much more variations, almost twice through 3 times and 4 times compared to the original variation. On the top right, we show the variations of all of those F2, F1, and the third, fifth, and seventh intermodulation products in time to show that how stable these intermodulated products are. And we have shown that when only the change in the F2 is observed, because that's what the frequency that is exposed to the environment, and F1 is constant in this case, the variations of the intermodulated products are not more than the original frequency, but in some cases it's even smaller. And we have shown that in the paper that we can achieve a much better characteristics when there is a small when these 2 frequencies are fed together immediately and there is no time delay between them. So that shows that the free moving behavior of the intermodulated products is not this noise is not going to exacerbate the sensing paradigm. This is shown actually in the phase noise behavior that is also both simulated and also measured as well, that the higher intermodulation product is going to show not worse, but sometimes better behavior as well. So we have used this technique for the material sensing, and we have tested for bulk medium of different types. We have shown that for all of them, the variations in the original sensor are going to be multiplied by 2, 3, and 4 when we're engaging higher intermodulation products. we have shown that in an in vitro glucose concentration measurement as well, the variations of the conventional oscillator could plateau at some point when glucose concentrations are going to be measured by from 0 to around 500, 600 milligram per deciliter. However, the seventh intermodulation product could show much more variations, still in the kilohertz range, that we could use in sensing applications. And remember that all of these variations are such small that none of those passive resonators could help us get there. In another experiment, we could show that in oil precipitation sensing, also the variations are noticeable, such that with the use of this technique of seventh intermodulation product, we could go down to 62 ppm and 6 ppm distinctly separable from each other when such small variations of asphaltene are going to be precipitated and distinguished. And also we have developed, and here's only an application on the active sensors in practical scenarios where the glucose sensing is of importance, because there's a large number of people who are affected by being impatient of high glucose level in their blood, and they need to be monitored continuously. However, the typical and conventional electrochemical sensing mechanism is sometimes painful for the kids and also elderly people, because they need to prick the finger and to get a blood sample and test that, and that's not a single time measurement. However, we proposed a technique that we could employ active sensors that are going to be wearable, and they could continuously monitor the variation of the glucose level, not only in continuous form factor, but also in a non-invasive form factor, because in that case, you're not going to prick any finger, and the resonator is going to wirelessly intercept the material inside the interstitial fluid or what is under the skin. That's one of the applications that we have shown in vitro examples, that with various types of the sensor that is shown with different bias voltages, we could show a reliable sensor response for a wide range of glucose concentrations over here from 100 millimolar all the way to 1,000 millimolar. And at the bottom, we can show much more sensitive region of the sensor for smaller concentrations, all the way from only saline solution out to 30 millimolar, which are in the range of typical people's normal glucose level in blood. So this is achievable in the sub-megahertz, in the kilohertz range. That is almost impossible to be achieved with passive sensor. However, active sensor allows us to distinguish such small variations. I guess in the interest of time, I would like to pass on these wireless communication that we have developed for the active sensors, but we can go back later. However, I would like to touch upon a little bit of the machine learning before finishing it up. So we have tried sensing materials non-invasively when the material is going to be placed in a distant with respect to the sensor, and that happens for distances in the range of centimeters. However, chances are that the sensor distance to the material is not exactly the same for all cases in harsh environments, and there could be some variations. And these variations could lead us to different forms of the sensor response. In our case, if the sensor response is going to be elaborated with frequency of resonance, amplitude of resonance, and quality factor, and they are going to be laid out here, you can see that for different materials, we have different versions of quality factor, versions of amplitude, or of the frequency of resonance, even if they are all for the same material. But because the material is placed slightly at a different location compared to the sensor, we'll get different result. In this case, this scrambled sensor response doesn't help us to distinguish the material itself, because there might be 2, 3 materials that are mixed with each other, and we can't recognize which is which, even if they are different materials, but they are placed at a different location. Over here, we have used a fuzzy neural network in order to help us to get the information of not only the frequency and quality factor and amplitude, but also all of them in combination with each other. And in order to, and before any use of optimization in the fuzzy neural network, we were hoping that all of these samples that are laid on these 4 groups to be mapped into these green boxes over here. However, we could see that that is doable much better when there is an optimization on the fuzzy neural network that helps us to move those points outside these boxes and into the boxes. And our mapping accuracies are given here, and comparing the different mapping accuracies show an average improvement of from 49% accuracy all the way to 81% accuracy. So this shows that how the use of machine learning helps us to better focus the power, focus the sensing response into the material itself. In another experiment, we have deployed active sensor for the sensing of the temperature of the environment, for the sensing of the material itself in different temperatures. And we found out that the temperature itself could change the sensor response significantly in some cases, that you can see that the frequency of operation could have some overlaps with each other. And in some cases, you can't really distinguish which is which. Some material at higher temperature shows the same response as the other material at much lower temperature. So that shows the adverse impact of the temperature on a sensor. In order to resolve this, we have used machine learning in order to check not only the resonance frequency, but also the whole profile of transmission response to the sensor. In that case, we have first analyzed a wide range of material properties for a wide range of temperatures as well, in terms of the acetone, methanol, but there are different concentrations, and you can see that how their frequency response overlap with each other. And also a single material at different frequencies shows this much of overlapped behavior. We have analyzed all of them at different frequencies and found out the contribution of the substrate itself and the MUT and their combination. And we found out that not only the MUT changed the temperature, but also the substrate changed the temperature, as you can see here. And what we did is we have fed different classes of materials, which classes actually denote different materials at different temperatures. So class 1 shows material 1 at different temperatures, class 2, material 2 at different temperatures, and all of them are fed into a classifier, and in that case, around 5,001 points of the S21 is input to the system. This helps us to at the first stage of this analysis to classify a given input signal into a different material type. And then we can find out that actually what the material is with respect to different classes. Once each class is known, then we were using a regression in a second stage to be able to find out at what is the temperature of an associated measurement is. So essentially, we're coupling two machine learning techniques. One is the classifier and one is the regressor, such that with coupling them, we can not only distinguish the material under test, but also we can also find the temperature of the measurement. And in that case, we can easily identify the material in different scenarios, even if the material, the environment temperature is not constant and is not known. So that's pretty much everything about my presentation. Here are some of the references that I have used. I might go through this conclusion briefly. Ultra-high sensitive passive sensors are achieved with increased coupling for both material characterization and mechanical displacement sensing. Active sensors are devised to improve quality factor in sensitive measurements. Regenerative amplifiers are used to partially compensate the loss factor power. Full compensation is obtained using microwave oscillator designs. The oscillator phase noise being reduced using active filter. Sensitivity of material categorization is increased arbitrarily with exploiting intermodulation products. Wireless communication is enabled with active sensors, and the robustness of planar sensors is increased with machine learning algorithms. With that, thank you so much for your time, and I'm ready to take any questions if there is any. Thank you.
Thank you very much. Thank you, Mohammad. It was very, very interesting and inspiring to
Yeah.
learn about a variety of techniques which can be used to enhance the otherwise limiting sensitivity of microwave sensors. So I have myself a couple of questions. I'm trying meanwhile monitoring if our attendees have any raised hand or questions. So let me go to the list of mine questions first, and we'll see how other people join. I'm wondering about the. I like the way how you can, if there are more than one thing, it's varying at a time. So, for example, either the position of the sample and the material, all the temperature and the materials varied. That how you can use the variety of machine learning technique to distinguish the two. So I'm wondering, for example, for these example when you had a material in the tube close to the sensor and they vary the position. So what's the, let's say, the range of distances you use to kind of smear the measurement? So was it like on a millimeter range or centimeter range?
Yeah.
You know, to.
So when we are actually placing the initial distance was around 5 centimeters of the initial sample from the sensor itself. But then when we tried for a given sample, we tried to place them in a millimeter size, the different deviations, either in the lateral direction or in the X direction or Y direction. So that it could just show different sense placement, because typically in real case scenarios, there's no guarantee that your sensor is going to be exactly at the same location all the time. Otherwise, you have to implement a specific type of arrangement for the configuration stability.
Right. So here also, it of course depends on the way of how it sends, but if you use VNA with the whole curve, also probably you could use a whole profile to try and count not only the quality factor and amplitude, which is of course, well, simplest things to try, and what do you have? Amplitude, quality factor, and frequency, right? So 3 dimensions, but you can have more, of course, probably to try to see. But that would be also interesting to see how far you can go with the scrambling of the position to still be able to distinguish what is the material, because I believe there might be some combinations of parameters of these 3 parameters to create ambiguity. But if you would go for maybe for a whole profile, that could be, or potentially more sensors, you know, we can have 2 orthogonal, then it could be actually very powerful to distinguish not only the position but also well, not only the material, but maybe you can use it to decrease ambiguity if you have, like, say, sensing in a free maybe, let's say, free axis, or let's say to say free sensor, 2 sensors combined. But just curious. It's really interesting indeed.
Yeah.
So my other question, this is maybe, here, exactly this slide. I'm wondering, what's the frequency here on the axis on the right? So is it really the frequency, or what is the units there? Or maybe
so indeed, this is I guess there's a typo here. The frequency variation in the megahertz range. So
it's
all of those are the frequency variation from the original value.
Okay, so it's just the delta F in megahertz. Okay, so it's like no sub-terahertz measurement or something. Okay, cool. I see Cristiano Palego raised a hand, so Cristiano, I'll make you a presenter, so you can unmute yourself and also show if you like. So Cristiano, go ahead with your question if you like.
Great. Can you hear me?
Perfectly.
Yeah, sure.
Hi.
Hi. Thank you for the very interesting presentation. I like the fact you propose different approaches, and there's multiple ways to increase sensitivity. I was wondering, do you have like a rule of thumb to compare to, for example, previous work? Like especially this might be a little a little too coarse, but in terms of minimum capacitance, you can sense. Like I know if I'm using a pretty decent, VNA, I can probably go down to 0.1 femtofarad. If I start to use, I don't know, a micro interferometer based approach with some lock-in amplifier like University of Manitoba, probably I get to the tens of attofarad range. And then if I use, for example, injection locked amplifier oscillator kind of approach, maybe I get to the attofarad range. Do you have any similar metrics for your approaches? And then I also appreciate the fact that you might actually be able to have a simpler architecture than in other in previous work. So I definitely appreciate that component. But would you have any metrics in terms of capacitance you can measure with the different approaches?
Yeah. Thanks for the question. So in terms of the measurement of the capacitance values based on the simulation results and comparisons that we have done, what we did was for a given set of material variation and material change. And what we found out is that when a certain material is going to be introduced to the sensor, the capacitance changes in the range of around 5-10 femtofarads up to 50 femtofarads. So that's the range of the capacitance variations that maps with the material variation. So that's the region that we are mostly working, and I think that in the range of femtofarads, and the single-digit femtofarads probably is the limit that we can work with these techniques, especially considering that any you need to consider the whole idea of the planar sensor that is exposed to the environment, and your other proximity variations could easily impact adversely on the sensor and reduce your robustness and stability. So essentially, if you want to increase this resolution and reduce the femtofarad range, you need to incorporate much more complicated casing or packaging to the sensor, such that all of that planar sensor is already encapsulated inside a metallic enclosure, for instance, that is immune from the environmental proximity impacts or electromagnetic behaviors. So what I can tell you is in the range of tens of femtofarads that we can improve the behavior of the sensor.
I see, but maybe it's because you're still having a relatively large volume. Like when you talk about the capacity gap for your split ring resonators, what kind of dimension are we looking at?
So the volume of the material, you mean?
Yes.
Really, it's in the range of
like
single digit.
The capacity gap there. How large was that?
Yeah, that distance is around 0.2 millimeter, so 200 micrometers.
Yeah. Okay. I think the kind of work I'm referring this really for single cell sensing, so it's more in the 20 micron as opposed to 200 micron. Okay.
True.
So I think that's potential for your approach, even in that regard. If you minimize the volume there, I think you can definitely go below the femtofarad.
Yes,
region.
That's a very good point. Our volume of the material in general is around in the single-digit microliters, so we're not actually shrinking the size that much. But yeah, the next step definitely could be a much smaller volume.
Great. Last thing, really quick. Can I see your reference list again? I just didn't have the time to read that.
Sure.
Great. Much appreciated. Thank you.
Yeah, no worries. Yeah, have a good one.
Okay. We have some question now in the chat. So Mohammad, if you can open the chat. So one is from, can't really read the name because it's like just a acronym, but question is there, how did you calculate the feedback length for adding the amplifier? I mean, how did you come to know 20 millimeter is the appropriate length required for constructive addition? I tried to replicate this paper, but faced this problem. that's actually good. Somebody try to replicate that. So
Yes.
yeah, please, if you can have any comment on that.
Yes, sure. So let me. Okay, so I guess this slide could best help us resolve that question. So essentially, what we care about in terms of the length of these transmission lines, in both cases of the amplifier, active resonator, or the oscillator, what we care about is the full constructive interference of the wave that is sampled from the resonator and also is returned back. So we need to we can't really tell quite clearly because some of the parasitics could impact on that one. We need to get to this result with simulation. But as a rule of thumb, we need to find out that what is the phase that is incurred in this path from the first part of this transmission line, and also the amplifier, and also the second part of the transmission line. And all of this should come together to a full 360-degree phase. So if we consider that this amplifier has a phase of 180 degrees, so the combination of these two transmission lines should help us get to the total phase of 180 degrees, so that it could cancel out actually the impact of the amplifier. And that goes back to the length of these transmission lines, as well as the properties of the substrate, and also the parasitics that are involved actually over here, that sometimes they could change. But that's the rule of thumb that you need to start with and continue with the simulation of sweeping the values of these lengths to be able to find out the optimum point.
Okay, I hope it answered the question. Another one we have in the chat from Abdolrazzaghi. She's asking that how to or in which configuration we can stabilize the active device. That's a very general question, but I mean, we can comment on that.
Yes. So the active device actually, there are indeed two regions of operation for the active device that we briefly discussed that, and one of them is this active resonator. As you can see here, that there's no oscillations involved here. So if you're actually partially compensating the loss, there's no issue in the stability of that active device. Mostly the variations is much smaller than the environmental variations that we care about. However, for the cases that we are interested in, the oscillation behavior, that we increase the loss compensation mechanism. So there are some techniques. So one is increasing the quality factor of the tank that we discussed actually in one of the designs. And we elaborated at how incorporating the active tank could help us to stabilize the sensor better. So that's one of the circuit techniques that we can implement. However, we need to be, again, mindful that the whole sensing is exposed to the environment, and it's much better to encapsulate the sensor with metallic enclosures in practical and industrial applications, so that we could do away from environmental parasitics. That could help us stabilize the sensor much better. So these are some of the ideas that I can present, both in terms of the circuit design and also implementation wise.
Okay, thank you very much. Oh yeah, she said that. Okay, thank you. So that's great. Good. I have some more questions, if I may.
Yeah, sure.
These intermodulation products, that's very interesting. How you can actually, as you said in the end, is maybe a little bit boldly, you can arbitrarily scale the sensitivity. So I have maybe some related questions to those. At first, maybe if you could go to one of these circuits, I'm trying to understand what generates these, which component is responsible for generating these intermodulation products. So where is the nonlinearity, which does that? Just to.
So yeah, this is probably a good slide to talk about that. So over here you can see that we have two stages of the design. One is the active resonator over here that is using a bandpass filter. That this bandpass filter is again this resonator, the typical SRR resonator. And then we
Okay.
have a transistor over here that is in the feedback path and helps us actually to get an active behavior. So
Okay.
apart from that, there is another oscillator session that comes before that, and this oscillator could be similar to the active resonator itself.
Okay.
That mixing behavior is is happening because of these two frequencies of F2 and F1 that are
Okay.
coming to meet each other actually at
I see.
the base emitter part of this transistor.
So it's a
And that
transistor.
creates, yes, this creates
Okay.
the nonlinear products as you can see here.
Interesting. Okay, interesting. So I mean, could this be a crucial part? And let's say if you like to enhance the sensitivity, the selection of the transistor. I mean, in terms of the capability to generate the well, the mixing basically of the frequencies. Could that be important factor, or you didn't really, just to take some whatever you had there, you didn't really play with that, like trying to select different transistors to have with different responses for intermodulation products? Was it something you considered?
So in terms of the selection of the transistor, it doesn't really matter actually which type of the transistor you would use, because it's in the nature of the transistor to exhibit
Sure.
nonlinear behavior. However, a couple of quick notes that we could be mindful of if you want to have a more stable result from the sensor is the lower the noise figure of the transistor is also linked to with the low phase noise of this whole operation at the very end. So if you have a low noise figure, a transistor that's preferred. Also, we need to consider that this transistor should have enough gain when at the frequency of operation to be able to compensate for all of the losses, and not only when there is no material, but also when there is material. So typically a relatively high gain and low noise phase actually are the two characteristics that could be looked into.
Okay, I see. And one more question I have related to this interesting design here. For the sensing, let me check. So the F1, F2, what was there? Maybe we had in other slides. What was the typical difference of these frequencies of F1 and F2? Is it like no? Okay, let me see. Maybe it's on the graph there.
So you mean in terms of the value?
Yeah. Just curious how much they differ.
Yeah, these two frequencies are around, like one of them is around 4.97 and one is
Okay.
5.02.
Yeah, so it's
roughly
these
two.
40 something of megahertz.
Yeah.
Okay.
The difference between them should be not very small, so that they couldn't show a pulling effect on each other for no good reason, because we are caring about the sensing. We want that sensing to happen actually because of the material, not because of the intrinsic properties of these two circuits that are coupled. So we care about that. However, they shouldn't be too far from each other as well, because if you increase this distance, the intermodulated products would happen actually at much further frequencies away, and those frequencies are going to fall out of the bandwidth of this resonator as well, and that reduces the amplitude of the generated signal. So you're getting into the noise floor. You're getting closer to the noise floor indeed.
Okay. So there is like definitely a range from both sides, like how far you can go in terms of how close and how far in this delta F between these two frequencies. Okay, cool. Thanks for the explanation. Cristiano, you have one more question, so go ahead, Chris.
I'm also very much interested in this work. How about why was this working around 5 gigahertz? What was the criterion for you?
Yeah, so you could actually, at that time, actually, we didn't consider that much about the FCC considerations of the frequency regulations. We just explored the research to see that how we can exploit this into the higher frequency. There is not much limit actually in the frequency of operation. You could definitely implement that at 2.4 gigahertz as well. However, the high frequency essentially comes with better sensitivity, because your sensing area is small compared to the sensor itself. Your internal capacitance is small, and your sensitivity could be higher when you're introducing the sensor to a given external material. So we were trying to exploit the internal high sensitivity behavior of the sensor itself.
Brilliant. Thank you.
Yeah.
Okay, good. So I think I'm kind of happy. I would okay, maybe, well, this may be a general question. In the beginning, you mentioned the humidity sensor. So I'm wondering how that, in that particular case, how that was orthogonal to the other changes which could be taking place in parallel. Like, it can be changes in concentration of the gases, changing of the temperature. That was one of the, I think, humidity sensor. I think it was slide 21. Yes,
Okay.
yes. So
This
since you have
gas
a
sensor.
converter, something converts this polyaniline polymer is the one which absorbs the moisture and probably changes its complex permittivity, right? So that's your sensing element in a way, which is then its permittivity is changed. It's sensed by the resonator structure. So I'm wondering how much is sensitive to the temperature.
Yeah, that's a good question. We indeed haven't studied that actually to different temperatures. I don't have like enough information to talk about this specific material, but we have collaborated with another group who were expert in the design of such humidity sensing polymers. And that was only exploited in how these polymers are able to absorb the environmental humidity. And I guess that's a question that needs to be explored further later.
Okay. Thank you. Indeed, very, very nice work.
Yeah, no worries.
So I'm
Thank
looking
you.
forward for the other things we'll bring in. So I think this was very inspiring for, I believe, for all of us who attended and listened, watched. So
Yeah.
I'll give, if there is any other questions from the attendees. I'm checking all the chat or Q&A. I don't see any raised hand. So it is, I'm going to stop the recording, and if anybody wants like to ask anything of the record, it can. So far for the recording purposes, thank you very much to all of you for attending, and also to you, Mohammad, for a wonderful talk. So
No worries. Thank you so much actually for inviting and having me.
Okay, thank you very much.
Yeah, I really appreciate it.
Thank you. And then I think it's okay. There's one of people are thanking in the chat, so that's great. So thanks a lot.
I really appreciate everyone who attended the meeting.
Yeah. So, and I think that's it. So have a good day, everyone, and see you in one of the upcoming webinars. Bye-bye.
Yeah, thanks. You have a great one.
Thanks, Mohammed. That was great.
Yeah.